take a look at an example problem where we're given a 32.5 gram cube of aluminum, initially at a temperature of 45.8 degrees Celsius, and I'm placing that into 105.3 grams of water at 15.4 degrees Celsius. What would the final temperature of both substances at thermal equilibrium become? The aluminum is hot, the water is cold. We're going to warm up the water but cool down the aluminum to reach the final temperature. We understand that heat lost from aluminum is heat gained by the water, and heat is found by calculating mc delta T. We have a 32.5 gram piece of aluminum metal. Aluminum has a specific heat constant we look up on our table, 0.903. 0.903 joules per gram degree Celsius. The temperature the aluminum started at is 45.8 degrees. It is going to go down to reach the equilibrium we'll call the final temperature, T sub F to represent final temperature. mc delta T for aluminum set equal to the mc delta T for water. The mass of the water, 105.3 grams. 4.18 joules per gram degree Celsius is our constant for water. And keeping in mind that the water is going to warm up, so the final temperature is actually a larger number than the 15.4. And I'll just show that by placing it first in the equation. Let's begin some algebra to simplify our left side and the right side. 32.5 times 0.903 is 29.3475. And I still have the delta T there, so I'll just represent that parenthesis. So all I've done so far is simplified the first two parentheses. 105.3 times 4.18 is 440.154. And I'll still show the parenthesis, TF minus 15.4. Let's now distribute through our parenthesis. I'll start on the left side. 29.3475 times 45.8 gives me 1344.1155 minus 29.3475 final temperature. I distributed through the parenthesis. Same strategy on the other side of the equals. All right, 440.154 times 15.4. And this is what we'll write on the right side of our equals. We have 440.154 TF minus 6778.3716. Again, just distributing through the parenthesis, and now we need to bring like terms to the same side of the equation. Let's bring final temperature to the right side to keep it positive, and we'll bring the number to the left side and keep it positive. So let's add, both sides are going to be added 6778.3716. And let's do that, and we'll just simplify what we have. So 1344.1155, adding to that a value of 6778.3716. This is showing 8122.4871. Alrighty, so that's eliminated the number from the right-hand side. We want to bring the variable to the right-hand side. So we're going to need to add 29.3475 to both sides of the equation. So what we're doing now is really eliminating the variable from the left and bringing it to the right side, and I chose that direction to keep it a positive number. 440.154 plus 29.3475. And that's showing me a value of 469.5015, and then my variable TF. To get the variable by itself, we're just simply going to divide. I'll divide both. That pen doesn't seem to be working well. Let me grab another. I'm going to divide by 469.5015. And you can see how that will isolate the variable TF. So I'll just hit on my screen 8122.4871 divided by 469.5015. And the final temperature is 17.3 degrees Celsius. Let's see if this number makes sense. The hot piece of aluminum started at 45.8 degrees Celsius. The cold water started at 15.4 degrees Celsius. The water warmed up a little bit. The aluminum cooled down tremendously. And that makes sense because we see that water has a very high specific heat. To warm up water takes an incredible amount of energy. The specific heat constant for aluminum, 0.9. Water has over a 4-time greater value, so this number indeed makes sense. 17.3 degrees Celsius solves our problem. We're then challenged in another practice where we have a hot piece of metal weighing 350 grams and we heat it up to 100 degrees Celsius. It's then placed in a coffee cup calorimeter containing 160 grams of water at 22.4 degrees Celsius. The water warms and the copper cools until the final temperature is 35.2. We'll calculate the specific heat of the metal and identify it from the list provided to the right. So here's what we know. The metal weighed 350 grams. We don't know its identity, so we're really solving for the specific heat constant. Its initial temperature was 100 degrees, and it cooled to 35.2. On the other side of our equation, the water weighed 160 grams. The heat constant for water is 4.18 joules per gram degree Celsius. The change in temperature for water would be represented by 35.2 minus 22.4 degrees Celsius. Final minus initial. Let's start some algebra. Let's simplify the right-hand side. 160 grams of water times 4.18 specific heat for water times the change in temperature, the difference between 35.2 and 22.4. So when I simplify the right side of our equal, I get 8560.64. I'll simplify what we can on the left side of the equation. The 350 grams of aluminum, or excuse me, of copper. No, we don't know what it is. I'm sorry. That's what we're trying to solve. Whatever metal it might be, we have 350 grams. I'll multiply that by the change in temperature,